Hello there, and welcome to Sleep Science Chronicles. Tonight, we turn our gaze towards something so vast that it stretches beyond imagination. A structure so immense that galaxies themselves are merely tiny points of light scattered along its threads. We are going to explore the cosmic web. This is the largest pattern in existence. It is the architecture of everything. If you could somehow zoom out far enough to see the entire observable universe at once, you would find that all the matter we know of, every galaxy, every star, every atom, is arranged in an intricate, interconnected network of glowing filaments and dark, quiet voids. Picture a three-dimensional web spun across billions of light years. Imagine threads of light so long that traveling along one at the speed of light would take hundreds of millions of years. At the intersections of these threads, great clusters of galaxies gather like dewdrops on silk, and between them, stretching across the dark, lie immense empty regions where almost nothing exists at all. This web was not designed. It was not built. It emerged slowly, patiently, from the very beginning of time, shaped by gravity, guided by invisible matter, and stretched ever wider by the expansion of space itself. It is the quiet scaffolding upon which the entire universe hangs. Tonight, we will trace its filaments and peer into its voids. We will discover how it formed, what holds it together, and what it tells us about the nature of everything. There is no rush. Let each idea settle gently as we drift through the grandest structure the cosmos has ever made. The cosmic web is not something you can see with your eyes. It is far too large and far too faint. But over decades of patient observation, astronomers have learned to map its shape, and what they have found is extraordinary. Galaxies are not scattered randomly through space. They are strung along invisible threads like beads on countless necklaces, woven together into a pattern that spans the entire observable universe. These threads are called filaments, and they can stretch for hundreds of millions of light years without interruption. Where filaments meet, matter piles up. Galaxy clusters form at these intersections, regions containing hundreds or even thousands of galaxies bound together by gravity. These clusters are the densest places in the universe, blazing with light and activity. But most of the universe is not filled with light. Between the filaments lie cosmic voids, enormous bubbles of near emptiness that can span hundreds of millions of light years across. In these voids, galaxies are rare. Silence reigns. Darkness stretches on and on. The cosmic web is shaped by forces we cannot see. Dark matter, the mysterious substance that outweighs all visible matter 5 to 1, provides the invisible framework. Ordinary matter, the gas and dust and stars we can detect, follows along, gathering where dark matter is densest, avoiding the places where it is sparse. This web has been growing and changing for nearly 14 billion years. It began as tiny ripples in the fabric of the early universe and slowly, inexorably, evolved into the vast network we observe today. And it is still evolving, still stretching, still shifting, still responding to the quiet pull of gravity and the relentless push of cosmic expansion. Let yourself settle in. Let the scale of it wash over you without needing to grasp it all at once. We have all the time we need. If these calm, curious explorations help you unwind or give you a quiet way to end your day, consider liking and subscribing. It helps others find their way here too, one sleepy soul at a time. But for now, let your shoulders soften, let your breath slow, and let's begin. The cosmic web is the largest known structure in the universe. It encompasses everything we can observe, every galaxy, every cluster, every void, woven together into a single interconnected pattern. There is no edge to this web within our observable horizon. It simply continues in every direction, filament after filament, void after void, as far as our instruments can see. If you could view the universe from a distance of billions of light years, individual galaxies would vanish into insignificance. What you would see instead is the web itself, a faintly glowing network of threads stretched across the darkness with dense, bright nodes where the threads converge and vast, dim bubbles where almost nothing resides. The term cosmic web was coined to describe this pattern because of its resemblance to a spider's web or a tangled network of neurons. The comparison is poetic, but also structurally apt. The web has nodes, connections, and empty spaces, much like many networks found in nature and mathematics. It is a pattern that emerges when gravity acts on matter over billions of years. The cosmic web is not static. It is slowly evolving, stretching as the universe expands, with filaments growing longer and voids growing emptier over cosmic time. The web we see today is a snapshot of a structure that has been changing since the universe was young and will continue changing long after our sun has faded. Mapping the cosmic web requires observing millions of galaxies and measuring their distances from Earth. By plotting these positions in 3 dimensions, astronomers can trace the outlines of filaments and voids. The result is a map unlike any other, a chart of the architecture of reality itself. The first clear evidence of the cosmic web came in the 1980s, when large galaxy surveys revealed that galaxies were not evenly distributed through space. Instead, they clustered along certain directions and avoided others, hinting at an underlying structure far larger than anyone had imagined. Modern surveys have mapped hundreds of millions of galaxies across billions of light years. Projects like the Sloan Digital Sky Survey have traced filaments stretching across significant portions of the observable universe. Each new survey adds detail to our picture of the web, revealing structures ever more intricate and vast. The cosmic web contains virtually all the ordinary matter in the universe. The galaxies we see are only the brightest, densest concentrations. Between them, along the filaments, vast quantities of gas drift in the darkness, too faint to see directly but detectable through its subtle effects on light passing through. The web is dominated not by what we can see, but by what we cannot. Dark matter outweighs ordinary matter by roughly 5-to-1. This invisible substance provides the gravitational scaffolding on which the visible web is built. Without dark matter, the cosmic web as we know it would not exist. Understanding the cosmic web helps cosmologists test theories about the universe's origin, composition, and fate. The precise pattern of filaments and voids depends on fundamental properties of matter, energy, and gravity. By studying the web, scientists can probe the deepest questions about reality. Filaments are the defining feature of the cosmic web. These are immense chains of galaxies and gas stretching across space, connecting galaxy clusters like bridges spanning an infinite ocean. A single filament can extend for hundreds of millions of light years, making them among the largest coherent structures in existence. Within a filament, galaxies are strung along the length like pearls on an impossibly long necklace. The spacing between galaxies varies, but the overall alignment is unmistakable. Galaxies within filaments are not randomly oriented. They tend to point along the filament's direction, their shapes subtly influenced by the larger structure around them. Filaments are not uniform tubes. They have varying thickness and density along their length. Some regions are rich with galaxies and glowing gas, while others are sparse and dim. The filament is a river of matter. And like any river, it has deep channels and shallow stretches. The gas within filaments is incredibly hot. Temperatures can reach millions of degrees, heated by the gravitational compression of matter falling inward. This gas glows faintly in X-rays, though it is so diffuse that detecting it requires sensitive instruments and long observation times. Most of the ordinary matter in filaments is not in galaxies at all. It exists as a thin, hot plasma spread along the length of the structure. The intergalactic medium. This plasma contains more atoms than all the stars in all the galaxies combined, yet it is so spread out that it barely registers against the darkness. Filaments can be thought of as cosmic highways. Galaxies do not just sit still within them. They move along the filaments, drawn toward the dense clusters at the intersections. Over billions of years, galaxies slide along these threads, slowly migrating toward regions of greater density. The longest filaments discovered span over 1 billion light-years. These immense structures dwarf anything else in the universe. A beam of light, traveling at the fastest speed possible, would take over 1 billion years to traverse such a filament from end to end. Filaments often connect the largest galaxy clusters in the universe. These clusters sit at the nodes of the web, and the filaments are the bridges between them. Matter flows along these bridges, feeding the clusters and allowing them to grow ever larger over cosmic time. The shape of filaments is influenced by dark matter. Because dark matter interacts only through gravity, it clumps together in ways that ordinary matter follows. The filaments we see in galaxies and gas trace the underlying filaments of dark matter, which are invisible but far more massive. Some filaments are relatively straight, stretching between two clusters like a taut string. Others curve and twist, bending through space in complex arcs. The shape depends on the distribution of mass in the surrounding region and the history of gravitational interactions over billions of years. Filaments are not isolated. They branch and merge, forming a tangled network that connects every part of the cosmic web. A single filament might split into two, or two might converge into one. The result is a structure of extraordinary complexity, with no clear beginning or end. Galaxies falling into filaments can be stretched and distorted by tidal forces. The gravitational pull is not uniform. It is stronger on the side of the galaxy, closer to the filament's center, and weaker on the far side. This difference can elongate galaxies, pulling them into cigar-like shapes aligned with the filament. The Milky Way itself is part of a filament. Our galaxy sits within a structure that connects several nearby galaxy groups. We are not at a major node of the cosmic web, but somewhere along a thread, drifting slowly through the larger pattern. Filaments contain not just galaxies, but also vast clouds of hydrogen gas that have never formed stars. These clouds are the raw material of the universe, primordial matter that has remained largely unchanged since the early cosmos. They drift along the filaments, waiting to fall into galaxies or clusters where they might one day ignite into stars. The density of matter within filaments is still remarkably low by earthly standards. Even in the densest parts, there might be only a few atoms per cubic meter. This is a better vacuum than any we can create in laboratories on Earth. Yet across such vast distances, even this sparse matter adds up to enormous total mass. Simulations of the cosmic web show filaments forming naturally from the initial conditions of the universe. Given the right starting point, tiny density variations in the early cosmos, gravity inevitably pulls matter into these thread-like structures. Filaments are not accidents. They are the natural consequence of physics operating over cosmic time. Where filaments intersect, the most dramatic structures in the universe arise. Galaxy clusters, collections of hundreds or thousands of galaxies, form at these nodes. These clusters are the largest gravitationally bound objects in existence, held together despite the expansion of the universe around them. Galaxy clusters can contain masses equivalent to 1,000,000 billion suns. Most of this mass is dark matter, forming an invisible halo that extends far beyond the visible galaxies. The galaxies themselves are like glitter, scattered through a vast, dark cloud, bright, but contributing only a small fraction of the total mass. The space between galaxies in a cluster is not empty. It is filled with the intercluster medium, a thin, hot gas that glows in X-rays. This gas has been heated to tens of millions of degrees by the violence of the cluster's formation and by the ongoing collisions and interactions within it. Galaxy clusters grow by consuming their surroundings. Galaxies fall in along filaments, adding to the cluster's mass. Smaller groups merge with larger ones. Over billions of years, clusters accumulate more and more matter, becoming ever more massive and dominant. The largest galaxy clusters contain thousands of galaxies spanning tens of millions of light years. These immense structures are rare. There are only a handful of truly giant clusters in the observable universe. Most clusters are smaller, containing dozens to hundreds of galaxies. At the very center of many galaxy clusters lies a giant elliptical galaxy. These central galaxies are the largest galaxies in the universe, containing trillions of stars. They grow by cannibalizing smaller galaxies that fall into the cluster, absorbing their stars and gas over time. Galaxy clusters are not peaceful places. Despite the serene appearance in images, clusters are sites of ongoing violence. Galaxies collide and merge. Gas is stripped from galaxies and heated to extreme temperatures. The gravitational forces at play are immense and relentless. Some galaxy clusters are still in the process of forming. These young clusters show signs of active merging, multiple concentrations of galaxies coming together, shock waves rippling through the intracluster medium, and structures that have not yet settled into equilibrium. The most massive clusters act as gravitational lenses, bending the light from more distant galaxies behind them. This lensing effect can magnify and distort the images of background galaxies, sometimes creating multiple images or long arcs of light. Astronomers use this effect to study both the clusters and the distant galaxies beyond. Clusters are connected by filaments in chains that span the universe. A single filament might connect several clusters in a row, like stations along a railway line. Matter flows along these connections, linking the nodes of the cosmic web into a single interconnected system. The cosmic web contains not just clusters, but also smaller structures called galaxy groups. Our own Milky Way is part of the local group, a collection of more than 80 galaxies bound together by gravity. Groups are like smaller versions of clusters, containing fewer galaxies and less mass. Galaxy groups are far more common than clusters. Most galaxies in the universe belong to groups rather than massive clusters. These groups are the building blocks of larger structures, merging over time to form clusters at the nodes of the cosmic web. The local group is itself part of a larger structure called the Virgo supercluster. Superclusters are collections of galaxy clusters and groups, loosely bound or simply associated by their positions in the cosmic web. They represent the largest scales at which matter is organized before dissolving into the uniform expansion of the universe. Beyond superclusters, the universe becomes remarkably uniform. At scales of hundreds of millions of light years, the distribution of matter evens out. There are no structures larger than the cosmic web itself, no superclusters or higher levels of organization. The web is the ultimate pattern. Voids are the other defining feature of the cosmic web. These are the immense empty regions between filaments, where matter is sparse and galaxies are rare. If filaments are the threads of the web, voids are the holes, the spaces where the web is absent. Cosmic voids are enormous. A typical void might span 100 million light-years or more. The largest known voids are several hundred million light-years across, making them among the largest structures, or rather, absences of structure, in the universe. Despite their name, voids are not truly empty. They contain some galaxies scattered thinly through the darkness. They also contain dark matter and gas, though at much lower densities than in filaments or clusters. A void is not a true vacuum. It is simply far emptier than its surroundings. The density of matter in voids is roughly 20% of the cosmic average. This means that while voids are not empty, they contain far less matter than the universe as a whole. The contrast between voids and filaments is stark. The difference between sparse scattering and dense concentration. Galaxies in voids tend to be different from galaxies in denser environments. They are often smaller, bluer, and more actively forming stars. Without the gravitational interactions and crowding found in filaments and clusters, void galaxies evolve in relative isolation, following their own quiet paths. Voids are not static. They are expanding, growing larger as the universe itself expands. Matter flows out of voids and into filaments, leaving the voids ever emptier. Over cosmic time, voids become more pronounced, the contrast between empty and filled regions growing sharper. The expansion of voids is driven by both cosmic expansion and gravity. The universe as a whole is expanding, stretching space, and carrying everything apart. At the same time, gravity pulls matter toward dense regions and away from sparse ones. Both effects work together to empty the voids and fill the filaments. Some voids contain smaller structures within them, thin tendrils of matter that thread through the emptiness, or small isolated galaxies drifting alone. These features are faint and sparse, but they show that even the voids are not perfectly uniform. There is structure at every scale. The Bode's void is one of the most famous cosmic voids discovered in 1981. It spans roughly 330 million light-years and contains far fewer galaxies than expected. When it was first found, some astronomers wondered if it was truly empty, but subsequent surveys have revealed a thin scattering of galaxies within. About 60 galaxies, where thousands might be expected. Voids may play a role in the acceleration of the universe's expansion. Some researchers have proposed that we might live in a region of lower than average density, which could affect our measurements of cosmic acceleration. While this idea remains controversial, it highlights how voids are not just empty spaces, but potentially important players in cosmology. The shapes of voids are complex. They are not simple spheres, but irregular bubbles with varied boundaries. The edges of voids are defined by the filaments that surround them, so void shapes depend on the arrangement of nearby structures. Some voids are nearly round, while others are elongated or oddly distorted. Voids occupy most of the volume of the universe. Although filaments and clusters contain most of the mass, they are concentrated in a small fraction of space. The majority of the universe's volume is void, vast, dark, and nearly empty. When you look at the cosmic web, you are looking mostly at absence. The interiors of voids are among the most pristine environments in the universe. Matter there has experienced fewer gravitational interactions and collisions than matter in denser regions. Studying void galaxies can reveal how galaxies evolve when left largely undisturbed by their surroundings. Voids can act as windows to the distant universe. Because they contain less matter, light passing through voids is less likely to be absorbed or scattered. This makes voids useful for observing very distant objects, though the effect is subtle and requires careful analysis. The boundary between a void and a filament is called a wall. These walls are sheets of galaxies and gas that mark the transition from emptiness to structure. Walls can span tens of millions of light years, forming the surfaces of cosmic bubbles. One of the most famous walls is the CFA2 Great Wall, discovered in 1989. This structure is a sheet of galaxies stretching over 500 million light-years, forming part of the boundary of several cosmic voids. Its discovery was a landmark in our understanding of large-scale structure. Even larger is the Hercules Corona Borealis Great Wall, a vast structure that may span over 10 billion light-years. If confirmed at this scale, it would be one of the largest structures ever identified. However, structures this large push against our understanding of how the universe should be organized. The existence of very large structures raises questions about the cosmological principle, the assumption that the universe is uniform on large scales. While the cosmic web shows patterns of filaments and voids, these patterns should average out at sufficiently large distances. Structures that seem too large challenge this assumption. Walls and sheets are often overlooked in favor of filaments and clusters, but they are essential parts of the cosmic web. They form the two-dimensional surfaces that enclose voids, connecting filaments into a three-dimensional network. Without walls, the web would lack coherence. The cosmic web is sometimes described as resembling a sponge. The filaments and walls form the solid part of the sponge, while the voids are the holes. This analogy captures the three-dimensional, interconnected nature of the structure. It is not a simple pattern of dots and lines, but a complex, volume-filling network. Computer simulations of the cosmic web reproduce this sponge-like structure with remarkable accuracy. Starting from the conditions of the early universe, simulations can generate webs that match observations in statistical detail. This agreement gives scientists confidence that they understand the basic processes shaping the web. The cosmic web we observe today is only the visible part of a larger story. Much of the web is made of dark matter, which we cannot see directly. The visible galaxies and gas trace the underlying dark matter structure, like snow on invisible mountains. The true web is hidden, and we see only its bright decorations, Dark matter forms the skeleton of the cosmic web. In the early universe, dark matter began clumping together first, creating the gravitational framework that ordinary matter would later follow. Without dark matter, the cosmic web would not have formed. Ordinary matter alone could not have created such large structures in the available time. The nature of dark matter remains one of the great mysteries of physics. We know it exists because of its gravitational effects, but we do not know what it is made of. It does not emit, absorb, or reflect light. It interacts with ordinary matter only through gravity. Despite decades of searching, no dark matter particle has been directly detected. Dark matter filaments are denser and more continuous than visible filaments. The visible galaxies are concentrated in the densest parts of dark matter filaments, where gravity has pulled ordinary matter together most effectively. Between these bright spots, dark matter continues in an unbroken thread. Simulations suggest that dark matter filaments are remarkably thin compared to their length. A filament might be millions of light-years long, but only a few 100,000 light-years wide. These proportions give the cosmic web its characteristic stringy appearance. The gravitational influence of dark matter filaments extends beyond their visible boundaries. Galaxies feel the pull of the filament even before they enter the visible structure. This pull can align galaxies' spins, orient their shapes, and guide their motions long before they formally join the filament. Dark matter also forms halos around individual galaxies. These halos extend far beyond the visible stars and gas, enveloping each galaxy in an invisible cocoon. When galaxies interact within filaments, their dark matter halos touch and influence each other, often before the visible parts come close. The interplay between dark matter and ordinary matter is subtle and complex. Ordinary matter can cool, condense, and form stars in ways that dark matter cannot. This gives ordinary matter a different distribution than dark matter, concentrating in smaller, denser structures within the dark matter framework. Hot gas in filaments traces the dark matter structure but does not follow it exactly. Gas can be heated by shocks and feedback from galaxies, pushing it away from the densest regions. This creates offsets between the gas and dark matter distributions that astronomers can use to study both components. Gravitational lensing provides one of the best ways to map dark matter in the cosmic web. By measuring how the light from distant galaxies is bent and distorted, astronomers can infer the distribution of mass along the line of sight, including the invisible dark matter. Weak gravitational lensing surveys have revealed the dark matter cosmic web in stunning detail. These surveys measure the subtle distortions in millions of background galaxy shapes, combining them to create maps of the foreground mass distribution. The resulting images show filaments and clusters traced in dark matter. One of the most ambitious weak lensing projects is the Dark Energy Survey, which has mapped the dark matter distribution across large portions of the sky. These maps confirm the predictions of simulations and reveal the intricate structure of the cosmic web's dark skeleton. The cosmic web began forming very early in the universe's history. Within the first few 100 million years after the Big Bang, the seeds of the web were already present, small variations in density that would grow into filaments and clusters over cosmic time. These initial density variations originated even earlier, during the first fraction of a second after the Big Bang. A process called cosmic inflation stretched tiny quantum fluctuations to cosmic scales, creating the slight unevenness in matter distribution that gravity would later amplify. The density variations left an imprint on the cosmic microwave background. The ancient light from when the universe was only 380,000 years old. By studying this light, astronomers can see the primordial seeds of the cosmic web, frozen in time from the early universe. The spots in the cosmic microwave background correspond to regions that would become clusters and voids. Slightly denser regions appear as warmer spots. Slightly less dense regions appear as cooler spots. These tiny temperature differences, measured in millionths of a degree, mapped the future structure of the universe. From these small beginnings, gravity took over. Denser regions attracted more matter, becoming denser still. Less dense regions lost matter to their surroundings, becoming emptier. Over hundreds of millions of years, this process of gravitational amplification transformed tiny variations into the vast cosmic web. The first structures to form were not galaxies, but dark matter halos. These invisible clumps provided the gravitational wells into which ordinary matter would later fall. Dark matter led the way, and ordinary matter followed. As ordinary matter fell into dark matter halos, it heated up and eventually cooled, condensing into the first stars and galaxies. These early galaxies were small and irregular, mere fragments compared to the great spirals and ellipticals we see today. But they were the seeds from which all later galaxies would grow. Early galaxies merged and combined, building larger structures over time. Small galaxies fell into larger ones. Groups formed and merged into clusters. The cosmic web grew more defined as matter concentrated along filaments and evacuated from voids. The cosmic web at early times looked different from the web we see today. Filaments were shorter and more numerous. Voids were smaller. The overall pattern was finer, like a tightly woven mesh that would gradually stretch and coarsen as the universe aged. As the universe expanded, the web stretched with it. Filaments grew longer. Voids expanded. Clusters grew more massive as they accumulated matter from their surroundings. The web became more pronounced, with sharper contrasts between dense and empty regions. This evolution continues today. The cosmic web is not a finished structure, but a work in progress. Galaxies are still falling into filaments. Clusters are still merging. Voids are still emptying. The pattern we observe is just one frame in a cosmic movie that has been playing for nearly 14 billion years. In the distant future, the cosmic web will look very different. As the universe continues to expand, and as dark energy accelerates that expansion, filaments will stretch and thin. Clusters will become more isolated, separated by ever-growing voids. The web will fade, its connections weakening until only the densest nodes remain. Eventually, galaxy clusters may become island universes, cut off from each other by expansion so rapid that light itself cannot bridge the gaps. The cosmic web will dissolve into isolated points of light, scattered through an infinite darkness. But that fate lies countless billions of years ahead. The rate at which the cosmic web evolves depends on the balance between gravity and cosmic expansion. Gravity pulls matter together while building structure. Expansion pulls space apart, stretching structure. The interplay between these forces determines how quickly the web changes. In the early universe, gravity dominated. Structures grew rapidly as matter collapsed into halos, galaxies, and clusters. But over the last few billion years, dark energy has become increasingly important, accelerating the expansion and slowing the growth of structure. Today, the cosmic web is growing more slowly than it did in the past. New clusters are forming less frequently. Filaments are thinning. The age of rapid structure formation is ending, and the universe is entering a quieter phase of gradual dispersal. Cosmologists can measure this slowdown by comparing the cosmic web at different epochs. By observing distant galaxies, they see the web as it was billions of years ago. By comparing these observations to the nearby web, they can track how structure has evolved and confirm that growth is indeed decelerating. The evolution of the cosmic web is one of the key predictions of the standard cosmological model. Simulations based on this model accurately reproduce the observed changes in the web over cosmic time. This agreement is a triumph of modern cosmology, demonstrating that we understand the basic physics shaping the universe. Different regions of the cosmic web evolve at different rates. Dense regions where gravity is strong continue to grow and accumulate matter. Sparse regions where gravity is weak are dominated by expansion and become emptier. The contrast between these regions increases over time. Galaxy clusters at the nodes of the web are still growing, slowly accreting matter from the surrounding filaments. Some clusters are doubling in mass over billions of years, consuming galaxies and gas that fall inward along the cosmic highways. The largest clusters today are approaching a maximum size set by the competition between gravity and expansion. In an accelerating universe, there is a limit to how massive a cluster can become before expansion prevents further growth. The most massive clusters we see may be close to this cosmic limit. Filaments connecting clusters can persist for billions of years, but they are not eternal. As expansion stretches them, they can become too thin to maintain their structure. Gas and galaxies may disperse, leaving only ghostly traces of former connections. Some filaments are being torn apart by expansion even now. These dying filaments are difficult to observe because they are so faint, but simulations predict their existence. They are the cosmic web's equivalent of fraying threads. Meanwhile, new filaments can form when clusters grow, and their gravitational influence extends to previously unconnected regions. The web is dynamic, with old structures fading and new ones emerging in an endless, slow dance. The cosmic web's evolution is influenced by dark energy in ways we do not fully understand. The nature of dark energy, whether it is truly constant or changing over time, affects how the web will develop in the future. Studying the web's evolution is one way to probe the mysteries of dark energy. If dark energy strengthens over time, the web will dissolve faster than expected. Filaments will tear apart. Clusters will be ripped from their connections. In the most extreme scenarios, even galaxies and atoms could be torn apart in a big rip. Current evidence suggests this is unlikely, but the possibility remains. If dark energy weakens, the web might stabilize or even begin to contract. Gravity could reassert its dominance, pulling structures back together. The web might thicken and strengthen rather than fade. This too seems unlikely based on current data, but the future remains uncertain. For now, the cosmic web continues its gradual evolution, stretching, thinning, concentrating, dispersing. It is a structure in motion, shaped by forces that have been at work since the beginning and will continue until the end of time. Between the galaxies, along the filaments of the cosmic web, lies a vast reservoir of matter that is almost invisible. This is the intergalactic medium, a thin, hot plasma that fills the space between galaxies and contains more atoms than all the stars in all the galaxies combined. The intergalactic medium is astonishingly sparse. In the densest parts of filaments, there might be a few hundred atoms per cubic meter. In voids, the density drops to less than 1 atom per cubic meter. By earthly standards, this is an almost perfect vacuum. Yet across the immense volumes of the cosmic web, this sparse gas adds up to enormous mass. Most of the intergalactic medium is hydrogen, the simplest and most abundant element in the universe. This hydrogen is not in the form of molecules or even neutral atoms. It is ionized, stripped of its electrons by the intense ultraviolet light that pervades intergalactic space. The temperature of the intergalactic medium varies depending on location. In the filaments of the cosmic web, the gas can reach temperatures of millions of degrees, heated by shocks as matter falls inward. In the voids, temperatures are lower but still far hotter than the coldest reaches of interstellar space. This hot intergalactic gas is difficult to observe directly. It emits very little visible light. Instead, astronomers detect it through its effects on other light sources. By the way it absorbs certain wavelengths from the light of distant quasars, or by the faint X-rays it emits in the densest regions. The intergalactic medium in filaments is sometimes called the warm-hot intergalactic medium, or WHIM. This gas, with temperatures between 100,000 and 10 million degrees, is thought to contain a significant fraction of all the ordinary matter in the universe. For decades, astronomers struggled to account for all the ordinary matter in the universe. They could count the matter in stars, galaxies, and hot cluster gas, but the total fell short of what cosmological models predicted. Something was missing, and the warm-hot intergalactic medium turned out to be the answer. The missing baryons, the ordinary matter that seemed to have vanished, were hiding in the filaments of the cosmic web. This gas is too hot to form stars and too cool and diffuse to emit detectable X-rays. It occupied a blind spot in our observations, invisible until new techniques revealed its presence. Recent observations have finally detected this missing matter. By studying the absorption of light from distant quasars and the subtle distortion of the cosmic microwave background, astronomers have confirmed that the intergalactic medium contains the expected amount of ordinary matter. The discovery of the missing baryons was a triumph for cosmology. It confirmed that our understanding of the universe's matter content is correct and that the cosmic web contains far more than meets the eye. The web is not just a pattern of bright galaxies, but a vast reservoir of hidden matter. The intergalactic medium is not static. It flows along filaments, falling toward clusters and feeding the growth of galaxies. This flow is slow by human standards. Gas might take billions of years to travel from a void to a cluster, but it is relentless and continuous. Gas falling into filaments is compressed and heated by shocks. These shocks form where infalling matter meets denser gas, converting the kinetic energy of infall into thermal energy. The resulting heat makes the intergalactic medium glow faintly in X-rays and other wavelengths. The intracluster medium, the gas within galaxy clusters, is the densest and hottest part of the intergalactic medium. Here, temperatures can reach hundreds of millions of degrees, and the gas glows brightly in X-rays. This gas has been studied for decades and provides important insights into cluster physics. Outside of clusters, the intergalactic medium is much more difficult to study. Its faintness and diffuse distribution make direct imaging challenging. most of what we know comes from indirect methods: absorption spectroscopy, gravitational lensing, and statistical techniques. The Lyman alpha forest is one of the most powerful tools for studying the intergalactic medium. When light from a distant quasar passes through intergalactic gas, hydrogen atoms absorb specific wavelengths, creating a forest of absorption lines in the quasar spectrum. By analyzing these lines, astronomers can map the distribution of gas along the line of sight. Each absorption line in the Lyman alpha forest corresponds to a cloud of hydrogen at a specific distance. By studying many quasars in different directions, astronomers can build up a three-dimensional picture of the intergalactic medium. This picture reveals the filamentary structure of the cosmic web in gas, as well as galaxies. The Lyman alpha forest shows that the intergalactic medium is not smooth, but structured. Gas is concentrated along filaments and sparse in voids, mirroring the distribution of galaxies and dark matter. The web is present not just in bright galaxies, but in the dim, diffuse gas between them. Heavy elements are present in the intergalactic medium, carried there by galactic winds and outflows. When stars explode or galaxies interact, they can eject gas enriched with metals, elements heavier than hydrogen and helium, into intergalactic space. These metals spread through the cosmic web, polluting the pristine primordial gas. The presence of metals in the intergalactic medium tells us that galaxies and their surroundings are not isolated systems. Matter cycles between galaxies and the intergalactic medium, flowing in and out over cosmic time. The cosmic web is not just a static backdrop, but an active participant in galaxy evolution. Some of the intergalactic medium will eventually fall into galaxies and form new stars. This gas represents the fuel supply for future star formation. Without the intergalactic medium, galaxies would quickly exhaust their gas and stop forming stars. The cosmic web sustains galactic life. In the far future, as the universe expands and cools, the intergalactic medium will thin even further. Gas will continue to fall into galaxies and clusters, depleting the reservoir. Eventually, the cosmic web will be emptied of its diffuse gas, leaving only the concentrated matter and bound structures. Observing the cosmic web is a formidable challenge. The structures are immense, spanning hundreds of millions of light years, but they are also faint and diffuse. Mapping the web requires patience, sensitivity, and clever techniques. The most straightforward approach is to map the positions of galaxies. By measuring the distances to millions of galaxies, using their redshifts as proxies for distance, astronomers can plot their three-dimensional distribution and trace the outlines of filaments and voids. Galaxy redshift surveys have been the workhorses of cosmic web cartography. Projects like the 2-degree field Galaxy Redshift Survey and the Sloan Digital Sky Survey have mapped millions of galaxies, revealing the web in unprecedented detail. These surveys have shown filaments stretching across billions of light years and voids larger than anyone had imagined. The Sloan Digital Sky Survey alone has measured redshifts for over 2 million galaxies, covering roughly 1/3 of the sky. The resulting maps show the cosmic web as a complex, three-dimensional network of structures, far more intricate than earlier surveys had suggested. New surveys are pushing even further. The Dark Energy Spectroscopic Instrument is measuring tens of millions of galaxy redshifts, creating the most detailed map of the cosmic web ever made. This map, will reveal fine details in the web's structure and help constrain the nature of dark energy. But galaxy surveys only show the bright parts of the cosmic web, the regions where matter has concentrated enough to form stars. To see the full web, including the diffuse gas and dark matter, astronomers need other techniques. Weak gravitational lensing reveals the dark matter structure of the cosmic web. By measuring the subtle distortions in the shapes of background galaxies, astronomers can infer the distribution of mass, both visible and invisible, along the line of sight. This technique has produced stunning maps of dark matter filaments. The Cosmic Evolution Survey and the Kilodegree Survey have used weak lensing to map dark matter over large areas of the sky. These maps show the cosmic web in mass rather than light, revealing the underlying skeleton that supports the visible structure. Weak lensing maps confirm that dark matter forms the backbone of the cosmic web. The dark matter filaments are broader and more continuous than the visible filaments, with galaxies concentrated in the densest parts. The visible web is just the tip of the iceberg. The thermal Sunyaev-Zeldovich effect provides another window on the cosmic web. When photons from the cosmic microwave background pass through hot gas in the web, they gain a small amount of energy. By measuring this energy boost, astronomers can detect hot gas even when it is too faint to emit detectable X-rays. The Planck satellite and other instruments have detected the Sunyaev-Zeldovich signal from filaments of the cosmic web. These detections confirm that hot gas pervades the web, connecting clusters and tracing the same structures seen in galaxies and dark matter. X-ray observations reveal the hottest parts of the cosmic web, the intracluster medium in galaxy clusters, and the densest parts of filaments. Satellites like Chandra and XMM Newton have produced detailed images of cluster gas, showing shocks, cold fronts, and other features that trace the dynamics of structure formation. Detecting X-rays from filaments is more challenging. The gas is hot but diffuse, producing faint emission that is easily lost in the background. Only a few filaments have been detected in X-rays, usually those connecting particularly massive clusters. New X-ray telescopes may reveal more in the coming years. Radio observations are beginning to contribute to cosmic web studies. The cosmic web contains magnetic fields, and electrons spiraling in these fields can emit radio waves. This emission is very faint, but new radio telescopes with unprecedented sensitivity may be able to detect it. The cosmic web may also be visible through the emission of hydrogen's 21-centimeter line. Neutral hydrogen in filaments and voids can emit radio waves at this characteristic wavelength. Detecting this emission would reveal the cosmic web in gas that is too cool to be seen through other methods. Hydrogen intensity mapping is a promising technique that aims to detect the collective 21-centimeter emission from many unresolved sources. By mapping fluctuations in this emission, astronomers hope to trace the large-scale structure of the cosmic web without needing to identify individual galaxies. The combination of multiple techniques, galaxy surveys, weak lensing, Sunyaev-Zeldovich measurements, X-rays, and radio observations, provides a comprehensive picture of the cosmic web. Each technique reveals different aspects of the web, and together, they show the full complexity of this immense structure. Future observatories will transform our view of the cosmic web. The Vera C. Rubin Observatory will survey the entire southern sky, detecting billions of galaxies and enabling weak lensing studies of unprecedented scope. The square-kilometer array will probe the cosmic web in radio waves, revealing neutral hydrogen and magnetic fields. The European Space Agency's Euclid mission is mapping the dark matter distribution across much of the sky using weak lensing. Its data will reveal the cosmic web in dark matter over a larger volume than any previous survey, helping astronomers understand the web's structure and evolution. As our maps improve, we are discovering that the cosmic web is even more complex than we imagined. Filaments have substructure, smaller threads within the larger structure. Voids contain faint tendrils of matter. The web is fractal-like, with patterns repeating at different scales. The cosmic web plays a crucial role in the lives of galaxies. A galaxy's location within the web, whether in a dense cluster, along a filament, or isolated in a void, profoundly influences its evolution, determining how it grows, how many stars it forms, and what shape it ultimately takes. Galaxies in dense environments tend to be different from galaxies in sparse environments. Cluster galaxies are more likely to be elliptical in shape, red in color, and low in star formation. Field galaxies, those in less dense regions, are more likely to be spiral, blue, and actively forming stars. This relationship between environment and galaxy properties is called the morphology-density relation. It was discovered decades ago and remains one of the most important patterns in extragalactic astronomy. The cosmic web provides the environmental context that drives this relation. Galaxies falling into clusters undergo dramatic transformations. Their gas can be stripped away by the hot intracluster medium, cutting off the fuel for star formation. Gravitational interactions with other galaxies can distort their shapes and trigger bursts of star formation, followed by quiescence. Round pressure stripping is one of the most important processes affecting cluster galaxies. As a galaxy moves through the hot intracluster medium, the pressure of the gas can push its own gas out, like wind stripping leaves from a tree. Galaxies can lose their gas reservoirs in a few 100 million years, quickly ending star formation. Tidal interactions also transform galaxies in dense environments. When galaxies pass close to each other, or to the center of a cluster, gravitational forces can stretch and distort them. Stars and gas can be pulled out into long tidal streams that trace the paths of past encounters. Galaxy harassment occurs when smaller galaxies experience repeated high-speed encounters with larger galaxies in a cluster. Each encounter imparts a small gravitational kick, gradually heating the smaller galaxy's stars and stripping its outer material. Over time, spiral galaxies can be transformed into dwarf ellipticals. Strangulation is a gentler process in which a galaxy's extended gas halo is stripped away, cutting off its supply of fresh gas but leaving its existing gas intact. The galaxy continues forming stars until its internal gas is exhausted, then gradually fades. This process can take several billion years. Galaxies do not only lose gas in clusters, they can also gain it. Galaxy mergers can deliver fresh gas and trigger new star formation. In some cases, cluster galaxies can accrete gas from the intracluster medium itself, though this is less common. The cosmic web influences galaxies even before they reach clusters. Galaxies falling along filaments begin experiencing environmental effects far from the cluster center. They encounter other galaxies, feel tidal forces, and may lose some gas to the warm-hot intergalactic medium. This pre-processing in filaments means that galaxies arrive at clusters already partially transformed. They may have already lost some gas, experienced interactions, or begun the transition from star-forming to quiescent. The cluster environment then completes the transformation. The spin of galaxies is influenced by the cosmic web. Galaxies tend to acquire angular momentum from the tidal torques generated by the surrounding mass distribution. In filaments, these torques tend to align galaxy spins with the filament direction, creating a subtle ordering of galaxy orientations. Observations have confirmed this alignment effect. Galaxies in filaments show a statistical tendency to spin in directions related to the filament axis. The effect is weak for any individual galaxy, but clear when many galaxies are averaged together. The shapes of galaxies are also aligned with the cosmic web. Elliptical galaxies tend to point along filaments, while disk galaxies tend to be perpendicular. These alignments reflect the gravitational influence of the web on galaxy formation and the anisotropic collapse of matter along preferred directions. Understanding these alignment effects is important for weak lensing studies. If galaxy shapes are intrinsically aligned, this can mimic or contaminate the lensing signal. Cosmologists must carefully model and correct for intrinsic alignments when interpreting weak lensing data. Galaxies in voids evolve differently from galaxies in denser environments. Without the interactions and stripping processes that occur in clusters and filaments, void galaxies develop largely in isolation. They tend to be smaller, bluer, and more gas-rich than their counterparts in denser regions. Void galaxies may represent a more pristine form of galaxy evolution. What galaxies would look like if left to themselves. By studying these isolated systems, astronomers can learn about the intrinsic processes of galaxy formation without the complications of environmental effects. The cosmic web also determines where galaxies form in the first place. Dark matter halos, the sites of galaxy formation, are concentrated along filaments and in clusters. Voids have fewer halos, and those that exist tend to be smaller. The web sets the initial conditions for galaxy birth. Star formation rates vary across the cosmic web. Galaxies in clusters have lower average star formation rates than field galaxies, reflecting the gas removal processes that operate in dense environments. Filaments show intermediate star formation rates, suggesting intermediate environmental effects. The quenching of star formation, the transition from actively forming stars to quiescence, happens more frequently in dense environments. Galaxies that were once blue and star-forming become red and dead as they fall into clusters and lose their gas. The cosmic web is a machine for transforming galaxies. Active galactic nuclei, supermassive black holes accreting matter at the centers of galaxies, may also be influenced by the cosmic web. Some studies suggest that AGN activity is enhanced in certain environments, perhaps triggered by galaxy interactions or gas infall along filaments. The cosmic web is not just a passive backdrop for galaxy evolution, but an active participant. It shapes galaxies through its gravitational influence, feeds them with gas along filaments, and strips them of gas in dense regions. The web and the galaxies within it are intimately connected. Matter in the cosmic web is not still. It is flowing, falling toward dense regions, streaming along filaments and emptying out of voids. These cosmic flows are among the largest coherent motions in the universe, carrying galaxies and gas across hundreds of millions of light years. The overall flow pattern is simple in principle. Gravity pulls matter toward the densest regions, toward clusters, toward filaments, away from voids. But the details are complex, with overlapping flows, turbulence, and chaotic motions superimposed on the general pattern. Galaxies participate in these flows. Our own Milky Way is falling toward the Virgo cluster, drawn by its gravitational pull. At the same time, we are part of a larger flow toward an even more massive concentration called the Great Attractor. The Great Attractor is a gravitational anomaly in the direction of the constellations Centaurus and Norma. It appears to be pulling hundreds of thousands of galaxies, including our own, toward it at speeds of several hundred kilometers per second. Its exact nature remains unclear, partly because it lies behind the plane of our own galaxy, where dust obscures our view. Beyond the Great Attractor lies an even larger structure called the Shapley Supercluster. This immense concentration of galaxy clusters may be the true source of the gravitational pull we feel. The Shapley Supercluster is one of the most massive structures in the nearby universe. These bulk flows, the large-scale motions of matter toward massive concentrations, provide evidence for the gravitational influence of the cosmic web. By measuring the velocities of galaxies, astronomers can infer the distribution of mass and confirm the existence of structures that may be difficult to observe directly. Peculiar velocities are the deviations of galaxy motions from the smooth expansion of the universe. Every galaxy participates in the Hubble flow, the general expansion that carries all galaxies apart, but each also has its own peculiar motion caused by local gravitational influences. Measuring peculiar velocities is challenging because it requires knowing both the galaxy's redshift and its true distance. The redshift includes both the cosmological expansion and the peculiar velocity, and separating these components requires independent distance measurements. Despite the difficulties, peculiar velocity surveys have revealed the large-scale flow patterns in our cosmic neighborhood. These surveys show that matter is streaming toward clusters and superclusters in coherent flows that span tens of millions of light-years. The Laniakea supercluster, defined in 2014, is the basin of attraction that contains the Milky Way. Within Laniakea, galaxies flow toward a common center, bound together in a coherent structure spanning over 500 million light-years. Beyond Laniakea's boundaries, galaxies flow toward different attractors. Defining superclusters by their flow patterns, rather than just their galaxy distributions, provides a more physically meaningful picture of the cosmic web. It reveals which galaxies are gravitationally connected and which are merely neighbors by chance. Cosmic flows also occur within filaments. Gas and galaxies stream along filaments toward the clusters at their ends, like water flowing downhill toward the lowest point. This flow feeds the growth of clusters and depletes the filaments over time. The velocity field of the cosmic web is not smooth, but turbulent. On small scales, galaxies orbit within clusters and groups, moving in complex, chaotic paths. On larger scales, bulk flows dominate, but there are still eddies and variations in the flow. Turbulence in the intergalactic medium can be driven by mergers, feedback from galaxies, and the accretion of matter along filaments. This turbulence affects the distribution of gas and can influence the formation of galaxies and stars. Cosmic flows were faster in the past, when the universe was smaller and denser. In the early universe, matter collapsed rapidly toward dense regions, building the first structures in the cosmic web. As expansion slowed and then accelerated, the flows weakened. Today, cosmic flows are being slowed by dark energy. As the expansion of the universe accelerates, it becomes harder for gravity to pull matter together. The largest flows are weakening, and the most distant structures are moving apart faster than gravity can pull them together. In the far future, cosmic flows will largely cease. The universe will be dominated by expansion, and only the densest bound structures, galaxy clusters and their contents, will remain gravitationally coherent. The web will freeze into isolated islands separated by expanding voids. The study of cosmic flows connects cosmology to the observations of our local universe. By mapping the motions of nearby galaxies, astronomers can infer the distribution of dark matter and test models of structure formation. The flows we measure today are echoes of the initial conditions set at the beginning of time. The cosmic web is not just a fascinating structure to observe. It is a powerful tool for understanding the universe. The precise pattern of filaments and voids depends on fundamental properties of matter, energy, and gravity. By studying the web, cosmologists can test their theories and measure the parameters that govern reality. The shape and size of structures in the cosmic web depend on the amount and type of matter in the universe. More matter leads to denser, more pronounced structures. Less matter leads to a sparser, more diffuse web. By measuring the statistics of the web, how many clusters, how long the filaments, how empty the voids, astronomers can infer the cosmic matter density. Dark matter leaves its signature in the cosmic web. The ratio of dark matter to ordinary matter affects how structures form and grow. Simulations with different dark matter contents produce webs with different properties. By comparing observed and simulated webs, cosmologists can constrain the nature and amount of dark matter. The cosmic web also probes dark energy. The growth of structure over time depends on the competition between gravity and cosmic expansion. Dark energy accelerates expansion, slowing the growth of structure. By measuring how the web has evolved, astronomers can study the effects of dark energy and test whether it is truly constant or changing over time. Borean acoustic oscillations are a particularly powerful cosmological probe encoded in the cosmic web. These are subtle patterns in the distribution of matter that originated as sound waves in the early universe. The waves traveled through the hot plasma of the early cosmos until it cooled enough for atoms to form, freezing the wave pattern into the matter distribution. The characteristic scale of baryon acoustic oscillations is about 500 million light-years. This means that galaxies today are slightly more likely to be separated by this distance than by other distances. The pattern is subtle but detectable in large galaxy surveys, appearing as a slight excess of galaxy pairs at this preferred separation. Baryon acoustic oscillations provide a standard ruler for cosmology. Because the scale is known from physics, measuring its apparent size at different distances reveals how the universe has expanded over time. This technique has become one of the most precise methods for studying cosmic expansion and dark energy. The cosmic microwave background and the cosmic web are intimately connected. The tiny fluctuations in the microwave background, the seeds of structure, evolved over billions of years into the filaments and clusters we see today. By comparing the two, cosmologists can trace the entire history of structure formation. The statistical properties of the cosmic web, how clustered the galaxies are, how the clustering varies with scale, how it has changed over time, encode information about the initial conditions of the universe. These statistics allow cosmologists to test models of inflation and probe the physics of the earliest moments. Neutrinos, the ghostly particles that barely interact with matter, leave their mark on the cosmic web. Neutrinos have mass, though very little, and this mass affects how structures grow. Massive neutrinos suppress the formation of small structures while leaving large structures relatively unchanged. By studying the cosmic web at different scales, astronomers can constrain neutrino masses. The cosmic web may also reveal new physics beyond the standard model. If dark matter has unexpected properties, if it interacts with itself, if it decays, if it has different masses in different regions, these effects would show up in the structure of the web. The web is a laboratory for testing fundamental physics on the largest scales. Modified gravity theories, proposed as alternatives to dark matter or dark energy, make different predictions for the cosmic web. By comparing observed and predicted structures, cosmologists can test whether Einstein's general relativity is correct on cosmic scales or whether modifications are needed. The cosmic web's sensitivity to cosmological parameters makes it a valuable complement to other observations. Combined with measurements of the cosmic microwave background, supernova distances, and other probes, studies of the cosmic web help build a comprehensive picture of the universe. The precision of cosmological measurements from the cosmic web continues to improve. As surveys map more galaxies over larger volumes and simulations become more accurate, the constraints on cosmological parameters tighten. The web is becoming an ever more powerful tool for understanding the cosmos. Computer simulations have revolutionized our understanding of the cosmic web. By modeling the evolution of matter under gravity over billions of years, scientists can watch the web form and grow, testing their theories against reality and predicting what future observations might reveal. The first cosmological simulations in the 1970s and 1980s used only a few thousand particles to represent the universe's matter. These early simulations were crude by modern standards, but they captured the essential physics: gravity pulling matter into clumps and filaments, voids emptying between them. As computers grew more powerful, simulations became more sophisticated. By the 1990s, simulations with millions of particles could reproduce the cosmic web in recognizable form. The filaments, clusters, and voids of the simulated universe matched observations with surprising fidelity. The Millennium Simulation, completed in 2005, was a landmark achievement. It tracked over 10 billion particles representing dark matter, following the formation of the cosmic web over 13 billion years. The resulting virtual universe contained millions of galaxies and reproduced the observed cosmic web in exquisite detail. Modern simulations go even further. The illustrious TNG simulation includes not just dark matter but also gas, stars, and black holes. It models the complex physics of galaxy formation within the cosmic web, producing virtual galaxies that look remarkably like real ones. These hydrodynamic simulations capture processes that dark matter-only simulations miss. They show how gas falls into filaments, heats up, cools, and forms stars. They reveal how feedback from supernovae and black holes reshapes the gas distribution. They connect the cosmic web to the visible universe. The largest simulations today use trillions of particles and require the most powerful supercomputers in the world. The Uchu simulation, released in 2021, contains over 2 trillion particles and models of volume spanning over 9 billion light-years. It provides the most detailed picture yet of how the cosmic web forms and evolves. Simulations allow scientists to run experiments that are impossible in the real universe. They can change the amount of dark matter, alter the properties of dark energy, or modify the laws of gravity, then watch how these changes affect the cosmic web. This virtual experimentation is essential for interpreting observations. By comparing simulations to observations, cosmologists can test their models and measure cosmological parameters. If the simulated web matches the observed web, the underlying model is likely correct. If they differ, the model must be revised. This feedback loop drives progress in cosmology. Simulations also reveal aspects of the cosmic web that are difficult or impossible to observe directly. They show the distribution of dark matter, the flows of gas along filaments, and the history of individual structures. They provide a 4-dimensional view, 3 dimensions of space plus time, that observations alone cannot achieve. The agreement between simulations and observations is one of the great successes of modern cosmology. The same basic model, general relativity, dark matter, dark energy, and initial conditions from inflation, reproduces the cosmic web from the earliest times to the present day. This concordance gives scientists confidence in their understanding of the universe. Simulations continue to improve. New algorithms capture physics more accurately. Faster computers allow larger volumes and finer resolution. Machine learning techniques accelerate the analysis of simulation data. The virtual cosmic web grows ever closer to the real thing. Future simulations will model the cosmic web with unprecedented realism. They will include more detailed physics, resolve smaller structures, and span larger volumes. They will help interpret the data from next-generation surveys, revealing the secrets of the cosmic web in ever greater detail. The cosmic web is connected to structures at every scale, from the largest superclusters to the smallest dwarf galaxies. Understanding these connections reveals how the universe is organized and how its different components influence each other. Galaxy clusters are the nodes of the cosmic web, but they are themselves complex structures. Within a cluster, galaxies orbit in a gravitational dance. The intracluster medium sloshes and heats, and dark matter forms a massive invisible halo. The cluster is a world unto itself, shaped by its location in the web. Groups of galaxies are smaller versions of clusters, containing a few to a few dozen members. Most galaxies in the universe belong to groups rather than massive clusters. Groups are the building blocks of the web, merging over time to form whole larger structures. Dwarf galaxies are the smallest and most numerous galaxies in the universe. They populate the halos of larger galaxies and the filaments of the cosmic web. Their distribution and properties provide clues about dark matter and the processes of galaxy formation. The halo of dark matter surrounding each galaxy extends far beyond its visible stars. These halos overlap and interact within filaments and clusters, creating a continuous distribution of dark matter that underlies the visible web. The boundary between one halo and the next is often unclear. Satellite galaxies orbit within the halos of larger galaxies, much as planets orbit stars. Our own Milky Way has dozens of known satellites, including the Large and Small Magellanic Clouds. The distribution of satellites is influenced by the cosmic web, with more satellites arriving along filament directions. Streams of stars trace the orbits of disrupted satellite galaxies. As a small galaxy falls into a larger one, tidal forces tear it apart, stretching its stars into long, thin streams. These streams are fossils of the web's influence, recording the history of accretion and interaction. The circumgalactic medium is the gas surrounding galaxies, extending beyond their visible disks, but within their dark matter halos. This gas is fed by infall from the cosmic web and shaped by feedback from the galaxy. It connects galaxies to their larger environment. Gas flows from the cosmic web into galaxies through the circumgalactic medium. These accretion flows bring fresh fuel for star formation, sustaining galaxies over cosmic time. The rate and direction of accretion depend on a galaxy's location within the web. Galactic winds and outflows return gas to the circumgalactic medium and beyond. When stars explode or black holes release energy, they can drive gas out of galaxies and into the surrounding space. This feedback enriches the cosmic web with heavy elements and regulates galaxy growth. The interstellar medium within galaxies is the gas and dust between stars. It is the site of star formation and the repository of stellar feedback. Though much smaller in scale than the cosmic web, the interstellar medium is connected to it through the cycle of gas flowing in and out of galaxies. Black holes at the centers of galaxies can influence their surroundings on enormous scales. Jets and outflows from active black holes can heat gas, suppress star formation, and even affect the distribution of matter in the cosmic web. The smallest and largest scales are linked through these powerful engines. The connection between the cosmic web and individual galaxies is a two-way street. The web shapes galaxies through gravitational forces, gas accretion, and environmental effects. Galaxies, in turn, shape the web through feedback, winds, and the ejection of enriched material. This interplay between scales makes the cosmic web a system rather than a static structure. Matter flows from the web into galaxies, is processed through star formation and feedback, and returns to the web enriched and transformed. The cycle continues over billions of years. The magnetic fields of the cosmic web are among its most mysterious properties. Magnetism pervades the universe, with fields detected in galaxies, clusters, and even the intergalactic medium. The origin and structure of these fields are still being explored. Magnetic fields in galaxy clusters are relatively strong, with strengths of a few microgauss, millions of times weaker than Earth's field, but significant on cosmic scales. These fields can influence the behavior of charged particles and the dynamics of the intracluster medium. Magnetic fields in filaments are weaker and harder to detect. Some observations suggest that filaments host fields of 1/10 of a microgauss or less. These fields may have been generated by early galaxies and spread through the web by outflows and motions. The origin of cosmic magnetic fields is debated. Some theories propose that weak seed fields were generated in the early universe, then amplified by turbulence and compression as structures formed. Others suggest that fields were created by astrophysical processes and spread outward from galaxies. Radio observations can reveal magnetic fields through their effects on polarized light and synchrotron emission. New radio telescopes are beginning to map the magnetic structure of the cosmic web, opening a new window on this hidden aspect of the universe. Cosmic rays, high-energy particles traveling through space, are influenced by the magnetic fields of the cosmic web. The fields can trap, deflect, and accelerate cosmic rays, affecting their distribution and the signals they produce when they strike the atmosphere. The cosmic web may be visible in gamma rays if cosmic rays interact with intergalactic gas. The resulting emission would be faint but detectable with sensitive instruments. Searches for this signal are ongoing and may reveal new information about the web's structure. Gravitational waves, ripples in spacetime produced by accelerating masses, travel through the cosmic web. The mergers of black holes and neutron stars produce gravitational waves that propagate across cosmic distances, passing through filaments and voids on their way to Earth. The cosmic web does not affect gravitational waves as it does light. Gravitational waves pass through matter almost unimpeded, carrying information about their sources without being absorbed or scattered. They offer a fundamentally different view of the universe. Future gravitational wave observatories may detect signals from mergers throughout the cosmic web, mapping the distribution of compact objects and testing theories of structure formation. The web that is invisible in gravitational waves may still shape the sources that produce them. Neutrinos also travel through the cosmic web, barely interacting with the matter they encounter. These ghostly particles carry information about the most energetic events in the universe, from supernovae to active galactic nuclei. The cosmic web is transparent to neutrinos, yet neutrinos help shape the web through their gravitational influence. The cosmic web connects phenomena across the entire electromagnetic spectrum. Radio waves reveal magnetic fields and hydrogen gas. Infrared light traces warm dust and hidden star formation. Visible light shows galaxies and stars. Ultraviolet light reveals hot gas and young stars. X-rays illuminate the hottest gas in clusters and filaments. Gamma rays may eventually reveal cosmic ray interactions. Each wavelength provides a different perspective on the cosmic web, and combining them gives a comprehensive view. The web is not one thing but many, a pattern visible in matter, light, gravity, and perhaps even particles we have not yet learned to detect. The cosmic web has a past and a future. We have traced its formation from the earliest times, watched it grow and evolve, and mapped its present structure. But what lies ahead? What will become of the web as the universe continues to age? In the near future, the next few billion years, the cosmic web will continue its gradual evolution. Clusters will grow as they accumulate matter from surrounding filaments. Filaments will thin as their matter drains toward the nodes. Voids will expand, becoming ever emptier. The Milky Way will continue its journey through the cosmic web. In about 4 billion years, it will collide and merge with the Andromeda Galaxy, our nearest large neighbor. The merger will create a new larger galaxy, sometimes called Milkdromeda, which will continue to orbit within the local group. The local group will eventually fall into the Virgo cluster, if it is not carried away by cosmic expansion first. The competition between gravity and expansion will determine whether we join a larger structure or drift into isolation. Current estimates suggest we may be near the boundary, making the outcome uncertain. On larger scales, the cosmic web will become more diffuse. Dark energy will continue to accelerate the expansion of the universe, stretching filaments and enlarging voids. The growth of structure will slow and eventually cease, frozen by expansion too rapid for gravity to overcome. In tens of billions of years, the cosmic web will begin to dissolve. Filaments will become too thin to maintain their coherence. Connections between clusters will break. The web will fragment into isolated island clusters separated by vast expanding voids. These island clusters will be the last gravitationally bound structures in the universe. Within them, galaxies will continue to orbit and interact, but the clusters themselves will be cut off from everything else. The universe will become a collection of lonely archipelagos in an infinite sea of darkness. Within each island, stars will continue to burn, but no new stars will form once the gas is exhausted. Old stars will fade, leaving behind white dwarfs, neutron stars, and black holes. The light of the universe will slowly dim as stellar furnaces run out of fuel. The white dwarfs will cool over trillions of years, fading from white to yellow to red to infrared to darkness. These crystallized stellar remnants will become cold. Dark spheres drifting through space, radiating the last of their heat into the void. Black holes will dominate the far future. The supermassive black holes at the centers of galaxies will consume surrounding matter and eventually each other. As galaxies merge within island clusters, their black holes will spiral together and coalesce into ever larger singularities. On timescales almost beyond comprehension, even black holes will fade. Through a process called Hawking radiation, black holes slowly evaporate, converting their mass into faint radiation over unimaginable spans of time. A black hole with the mass of the Sun would take far longer than the current age of the universe to evaporate completely. The largest black holes with masses billions of times that of the Sun will persist the longest. They will be the last significant objects in the universe, slowly radiating away over spans of time measured in Google years. One followed by 100 zeros. When the last black hole evaporates, the universe will enter its final state. A thin soup of particles and radiation, spread ever more thinly by endless expansion. There will be no structures, no patterns, no cosmic web. Only darkness, cold, and silence stretching forever. This fate, sometimes called the heat death of the universe, is the most likely outcome based on current understanding. It is not violent or dramatic, but quiet and gradual. A slow fading rather than a sudden end. Yet our understanding of the far future is limited. Dark energy may not be constant. New physics may emerge at scales or times we cannot yet probe. The ultimate fate of the cosmic web and of the universe itself remains uncertain. For now, the cosmic web exists in its full splendor. Filaments stretch across the darkness, connecting clusters of galaxies in a pattern that spans the observable universe. Voids expand between them, silent and nearly empty. Matter flows along the threads, feeding the growth of structures that have been building for nearly 14 billion years. We are part of this web. Our planet orbits a star in a galaxy that belongs to a group that sits within a supercluster that lies along a filament of the cosmic web. Every atom in our bodies was once part of this vast network, and every atom will return to it someday. The cosmic web is the largest pattern we know. It is the architecture of reality, the scaffolding of existence, the framework on which everything hangs. And yet, it is also ephemeral, a structure that emerged from chaos, exists for a cosmic moment, and will eventually dissolve into chaos again. There is something beautiful in this. The web is not permanent, but neither is it meaningless. It is a pattern that exists because the laws of physics allow it, because gravity pulls, because matter clumps, because the universe had just the right conditions for structure to form. We are witnesses to this pattern. For a brief moment in cosmic history, matter has organized itself into structures complex enough to wonder about their own existence. We are the universe contemplating itself, and the cosmic web is the grandest object of that contemplation. And so our journey through the cosmic web draws to a close. We have traced its filaments from the densest clusters to the emptiest voids. We have watched it form from tiny seeds in the early universe, grow through billions of years of gravitational collapse, and glimpsed its eventual fate in the far future. We have seen how the web is observed through galaxy surveys and gravitational lensing, through X-rays and radio waves, through the subtle absorption of distant light. We have seen how it is simulated in supercomputers that model the dance of dark matter and gas over cosmic time. We have discovered that the cosmic web is not just a pattern in space, but a participant in cosmic evolution. It shapes galaxies, channels matter, and encodes information about the fundamental parameters of the universe. It is both structure and process, both map and territory. The web connects us to everything. The atoms in your body were forged in stars that lived and died within this web. The light that reaches your eyes has traveled through filaments and voids for billions of years. The gravity that holds you to Earth is the same force that shaped the largest structures in existence. You are not separate from the cosmic web. You are part of it, a small, warm concentration of matter that has briefly become aware of the vast pattern surrounding it. When you look up at the night sky, you're looking at the web from the inside, seeing the light of galaxies strung along invisible threads. Tonight as you rest, the cosmic web continues its slow evolution. Filaments stretch, voids expand. Galaxies drift along their ancient paths. Somewhere, a cluster is growing. Somewhere else, a void is emptying. The pattern shifts imperceptibly, changing on timescales that dwarf human experience. And yet, for all its immensity, the cosmic web is gentle. It does not demand your attention. It does not require your understanding. It simply exists, a quiet backdrop to everything that happens, holding the universe together with invisible hands. Let yourself drift now, carried by these thoughts toward rest. Imagine yourself floating through the cosmic web, passing filaments of glowing gas, drifting between galaxies, moving through voids where almost nothing exists. There is no rush. There is no urgency. There is only the slow, patient unfolding of the universe across scales of space and time almost too large to comprehend. The cosmic web has been here for nearly 14 billion years. It will continue for billions more. Tonight, you are part of it. One small spark of awareness in a vast and ancient pattern. Tomorrow, the web will still be here, waiting for you to wonder about it again. If you are still awake, you can go ahead and watch the next video now. But if your eyes are heavy and your thoughts are fading, that is fine too. The cosmic web will keep its vigil while you sleep. The filaments will glow. The voids will expand. The universe will continue its quiet work. Sleep well and dream of the grandest structure the cosmos has ever made. Good night.